Yep, that's okay. Let's get started. Okay, so my name is Claire. So I'll be going through today's Set 3 Physics Revision lesson with you. So the lessons that I teach at Overmug, including lower set science, O-level and IP physics, and also JC physics. So a little bit about me. So I graduated from NTU and Raffles Institution, and I've been teaching tuition actually since right after my A-level and also throughout my university, and also after I graduate, I decided I will become a full-time tutor. So yeah, pretty much I've been like teaching since 2010. So some of the achievements last year, we managed to achieve a very impressive 100% A1 for my Set 4 IP class. So some fun fact about me, so I actually a cat lover. So I have 3 very fat British Shorthair at home. Yeah. Okay, so a little bit about this place, Overmug. So OVERMUGGED basically is one of the fastest growing tuition brand in Singapore. So currently we have more than 1,000 students every year, and we're expanded to 8 branches across Singapore. So of course we also have our presence like on the different social media. Okay, so we are well loved by our students because we deliver real results for them. So we actually achieve an impressive of 70% of our students achieve distinctions. And this is actually really the effort from our expert tutors, as well as like the community, like the learning environment that we cultivate here. And to help our students achieve all that, so of course, like the resources. So besides, so what you get, so for today's worksheet, right, is basically taken up from our created notes. And of course, right, you can also see like kind of the questions. So you get a sense of like the worksheet that we'll be going through. So of course, like besides like the regular lessons, we also have all the intensive revisions for the WAs as well as for the exams. And most importantly, also preparing for O-levels, the practical session, as well as the mock exam sessions. Okay, so the rest of the information I'll share after the class. So we will get started with today's revision. So the topic that we picked today, right, for set 3 is actually forces. So it's actually under our dynamics. So you will not be so much on so for today, you will not be so much on like going through a lot of concept and all that, because I believe most of you guys should be like, you have learned this in lower set and you have learned it again in set 3. So concept wise, understanding wise, I will assume will be quite okay. Of course, if there's anything you're not sure, feel free to ask me in the chat. And so for today's lesson, right, we will be actually focused more on the exam techniques. So in all the work examples, we're going to actually learn how to dissect, pick up information, and then we link it to the concept that we should be applying. So for forces, it's a push or a pull. An important thing here is to note that they are vector quantities. So like all the other vectors, they have both magnitude and direction. SI unit is in Newton. So when we draw it, okay, this is actually kind of like introduction for our free body diagram. When we represent the force, we use an arrow. So the length represent the magnitude and the direction given by the direction of the arrow. So these are some of the common types of forces that we actually considered when we're doing our questions. So our weight, tension, normal contact force, and friction. So in the first part, so we learn to distinguish between mass and weight. Okay, so fun fact, what we actually call commonly every day, like weight, like what's your weight or like a person's weight, right, is actually mass in physics. So the one that we actually measure in kilogram is actually mass. Okay, whereas weight in physics is actually referring to the amount of gravitational force acting on the body due to its position in a gravitational field. So then its unit, since it's a force, its unit is also Newton. So mass, on the other hand, right, is defined as the measure of the absolute amount of substance in the body. So in that sense, right, it's the amount of substance. So you can visualize it as the amount of atoms, ions, molecules, so the amount of substance inside the body itself. So because of that, right, like if you imagine like in this whole bunch here, we have 1 million atom. So this 1 million atom It doesn't matter where we shift it, where we put it, it will not change. So because of that, mass will always remain constant. So it's not affected by the place, it's not affected by time. Then whereas our weight, it is a force. And more importantly, this force is affected by the body's position in a gravitational field. So it will be affected if I place it. So if we change our object from Earth, let's say, then we bring it to the moon. So Earth and moon, right, we have a different gravitational field. And because of that, then the weight of the body will actually change. So that's why for our weight, it is not constant. It actually depends on the gravitational field strength at a point. So of course, to measure it, mass we use our beam balance, whereas our weight we use the spring balance. Okay. So to calculate our weight, we use this formula. So you box up W equal to mg. So take note that, so the G here is the gravitational field strength. So basically it tells you how many newtons. So for example, on Earth, our G is equal to 10 Newton per kg. So the meaning, the physical meaning of this means that for every kg of mass, you experience 10 Newton of gravitational force in Earth's gravitational field. Okay, so let's take a look at our first question. So take about 30 seconds to read the question. So our body have different weight on Earth and on the moon because of the difference in the gravitational acceleration, meaning our gravitational field strength. So orange with a mass of 150, so we can actually underline this orange has a mass and is 150 gram. It's found to have a weight of 0.24 on the moon. So if it's on the moon, right, our 10 is no longer applicable already because that one is only for, this is only for Earth. Okay, so we know that the orange, the mass of the orange, and we know the weight of the orange. So then next part, the weight of a metal ball at the same location on the moon is then measured using the same spring balance. The ball is found to have a weight of 50 Newton. What is the mass? So if we consider this question, because it's in the same place, it's in the same gravitational field. As we were mentioning earlier, so gravitational field, right, is affected by the location, very specific, the gravitational field that is in. So since both is actually measured on the moon using the same spring balance, so G should be the same. So then question, if we W equal to mg, if I want to make G the subject, what should I do with the m? Okay, if I want to make G the subject, because right now we want to equal the 2G, right? We should divide the mass over. So means that if I take the weight of the orange divided by the mass of the orange, it should equal to the weight of the ball divided by the mass of the ball. Just use B. So this will be the relationship. So when we're doing questions, right, always try to find out what is the formula and what is the relationship. Then we use it to form the equation. Once you have the equation, then you can start to sub in the value already. So I think we can get everyone 1 minute to try. So if you can try it, once you have the answer, then you can type in the chat. Very good. Some of you get the answer already. That is correct, but please remember when you type your answer, add in your unit as well. Because in test, if you only put the number without unit, you may get penalized. Yes, Chloe, that's correct. Okay, Xingyu, your answer is very off. Okay, so you want to check your working later. Okay, I got quite a few wrong answer here. So let me check where you guys get this. Okay, anyway, the correct answer should be 6.0 kg. Okay, so for all those of you get 3125, right? Okay, you may want to check your working. So I think some part go wrong. Okay, let's bring the values. So the weight of the orange, 0.24 Newton. Then mass of the orange, 150 gram. But remember, right, for our G, it's actually Newton per kg. So to make sure that the units are consistent. So I'm convert 150 gram to 0.150 kg. So on the other side, so the weight of the ball is 50 over mass of the ball. Okay, so from here to solve it, I do cross multiplied. So 0.24 MB should be 50 times 0.150. A moment now. Oh, I see. Sorry, those with 6.0, right? Yeah, I think there's something off. Sorry, the correct answer, mass of the ball should be 31.25 kg. So answer is not 6.0. So the answer actually will be 31.25 kg. Okay, let's move on to the next question. Okay, So for the next part, right, we'll be going through the 3 Newton's law. So for each of the law, right, we can remember it by one of the keywords. So for Newton's first law of motion, so the keywords for this law will actually be inertial. So first law is also known as the law of inertial. So the first law of motion states that all the object at rest will remain at rest. And if the object is in motion, it will continue in motion at constant speed. Okay. If it's already in motion, it will continue its motion at constant speed in a straight line. So in other words, it will continue to move with constant velocity, unless there is a resultant force acting on it. Okay, so basically, right, this keyword's inertial is describing the tendency of the body to continue its state of rest or motion. So inertial is dependent on the mass of the body. So if you're actually sitting in the car, if there is an emergency brake, our body will actually lean forwards. So this is because although there is a seatbelt holding us back, and although we are stopping, our body still have the tendency to move forward, and hence will lean forward, and because of the seatbelt, so will actually be constrained and will not be fall forward. So the heavier the body, the larger the inertial, and hence, right, it will actually be harder for the body to change its state of motion. Okay, whereas for our second law. So for our second law, the keywords or the key phrase we are looking at here is actually the resultant force. So the second law states that our resultant force acting on the object is basically equal to the product of the mass and acceleration. So if you summarize it, basically is Fr equal to ma. So one of the important thing to take note is a lot of time, right, student will just happily say that, oh, F equal to ma, but cannot be just be any forces. So in the body, if there are several forces acting on it, the one that equals to the product of mass and acceleration, right, is the resultant force, meaning the net force of all the forces acting on the object itself. So when we are doing our question, it's important to consider all the forces acting on it, and from there we can find the resultant force. Okay, so let's take about 1 minute. Take a look at the question first. So again, we can begin by underlining some of the key informations. We have the mass, that is 1.5 kg, being pulled horizontally from rest across a rough surface. So if it's a rough surface, means that there is friction acting on the body itself. And the applied force, 16 Newton. So given that the box reached a speed of 2.0 meter per second after moving 1.0 meter, what is the constant frictional force acting on the box? So looking at the frictional force acting on the box. So let's analyze the question. If this is my box, so we can sketch. So there will be the force that is pulling it, 16 Newton. Okay, then there will be the frictional force. So of course, right, there will also be the weight and there will also be the normal contact force. But in the way that we don't need to consider these two, because these two will balance already. So it's the applied force and the friction that's not balanced and cause the box to have a resultant force and hence an acceleration. So in that sense, right, if we link it together, To find the frictional force, I will need to know what is my applied force, and also I will need to know what is the resultant force. So you put them together. Our resultant force should equal to 16 Newton minus away friction. And to find our resultant force, Fr equal to Ma. So if we pause here, right, we see that I have the mesh already, and we're looking for the friction. So that means that we still need to find the acceleration. So then let's think, how do we find the acceleration from the question? What do we have here? We have the speed and we have the distance. So the speed actually increases from 0 to 2.0 meter per second. So if I have the change in speed already, we can actually use it to find our acceleration. Okay, let me try to ask the crowd. Okay, if I want to find my acceleration from the change in speed, which formula should I use? Which formula will allow us to find the acceleration from the change in speed? Alright, that's correct. So A should equal to V minus U over T. So in that sense that A already have V, U already, but we don't have time. Okay, so this will be the tricky part for this question. How do we find the time? So please resist the urge. I got distance, I got speed, go and divide. So you cannot take 1 meter divide by 2 because this is not constant speed. So I cannot take distance divide by speed to find the time. So then instead, we should actually use a speed against time graph to help us. So in this much of the time, the speed actually increased to 2.0. So the distance traveled, right, that 1.0 meter is actually equal to the area under the graph. So if you form the equation, area of a triangle, half times base times height. So half times t times 2.0 will equal to the area 1.0. So t will actually equal to 1.0 second. So once I have it, so we can use it to find our acceleration. So A will equal to 2.0 minus 0 over 1 second. So mass times acceleration will equal to the applied force minus away friction. So in the end, our friction will equal to 13 Newton. Okay, if everyone finished copying, then we can move on to question 3. If you still need to copy, you can let me know. Okay, otherwise we can move on. Can take a look at, I think let's take about 2 minutes, take a look at question 3, and then you can try first. So you can try question 3 first. Then once you have the answer, you can type in the group chat as well. Okay, I think let's go through question 3. So for question 3, right, when we're looking at these two boxes, it's important to consider when we do our free body diagram, which one are we looking at? So when they're connected here and when we have the 16 Newton pulling them together, first we can actually consider R and S together as a whole body. So in that way, we can actually ignore the forces acting in the string. And because the floor is actually frictionless, so there isn't any friction. So this 16 Newton will actually become the only force acting on the whole body. So this Fr will equal to Ma. 16 Newton will be the only forces. And the mass, because I look at this whole thing as a body, will be their total mass. So 6 plus 2, 8. So in that sense, our acceleration 16 divided by 8, so it'll be 2 meter per second square. So both R and S, they will be accelerating at this same value. So after that, if we just consider R alone, right? Then in that sense, the tension will be the only force acting on it. So this tension will equal to the resultant force. Then the resultant force, same thing, Fr equal to Ma. And now, because we are only looking at R, so the mass here should only be the mass of R. That's why 6 times acceleration 2. Yeah, and the answer will be 12 Newton. So this answer will be B. Okay, if everyone okay, they can move on and can try question 4 first. Okay, so this one, if you know the answer, you don't need to do any calculation already. So you can read the question carefully. Okay, we'll review the answer in a short while for question 4. So the hint is that this one you should be able to get the answer without any calculation. Okay, so for question 4, to reread it. So our car has a mass 300 kg moving at constant velocity. So guys, so constant velocity, this is very, very important keywords. So the moment you see this, right, that means that it's Newton's first law. When the object is moving with constant velocity or when the object is remain at rest, is in equilibrium. And the resultant force is equal to 0. So don't happily like 300 times 20, yeah, because this is not acceleration, this is velocity. Okay, and the constant velocity means that we're actually using Newton's first law, where resultant force is equal to 0. That's why the object is moving with constant velocity. So if Fr equal to 0 Newton, so the forces acting on the car right now should be able to cancel out each other. So the weight and the normal contact force cancel each other. The driving force and the friction should cancel each other. So it means that 0 should equal to the driving force minus away friction. So driving force is 5,000. So friction should also be 5,000 Newton. So let me know if you have any question. If not, then can move on and try question 5. So again, after you finish, you can type your answer in the group chat. Okay. Some of you got the answer, then some of you got a slightly different answer. Okay. Which actually I think is quite common. So like we say, so for this formula, FR equal to M8. Whenever you use this formula, make sure that this is the resultant force. So to get a resultant force, we need to consider all the forces acting on it. So for our mass right now, it has a tension, and don't forget, we has a mass, it has a weight acting on it as well. So the weight W equal to mg, 500 times 10. So there is actually a 5,000 Newton acting downwards. So from there, right, if you consider, so if you look at it, there is a 7,500 acting upwards, and there is a 5,000 Newton acting downwards. So overall, when we combine these two forces, it will give us a FR going upwards. So it should be 7,500 minus 5,000. So the resultant force is only 2,500. So then from here, we can use it to find our acceleration. Okay. So for those of you, if you just like straight away sub in 7,500, right, into this equation, then you will actually get 15. So that will be so that will not be correct because we didn't consider the weight. So be very, very careful. Like this our question, they just show you one force. Yep. So if you do too fast, then you like just fall into the trap. Okay, so those you get wrong, you can do the correction first. Then those get it correct, you can move on to question 6. Same thing will take about 2 minutes to try question 6 first. Then once you're finished, you can type your answer in the group chat. Again, when we're doing it, follow the previous approach. You can draw your free body diagram first. So at the beginning, when there is 24 Newton acting on it, and of course, from the surface, there is friction. So the box accelerates, so means that there will still be a FR. Then in the second case here, so we change the applied force. Okay, friction is the same surfaces, we can assume it's still the same. So this FR changed already, such that the acceleration now is 4 meters per second squared. So for the first one, and look at the relationship of these three. Can you actually use it to find your friction first? Then once you have friction, can we actually put it in the second part to help us find the applied force? If you're still not sure, then I think we can do this together. So this 24 Newton allow it to accelerate. So our resultant force, right, should be 24 minus away the friction. So then using the formula FR equal to MA. So mass is 6 kg, acceleration is 2. Okay, so acceleration is 2. So if we put it in, so you can work out that friction is actually 12. Then once you have friction, right, then we can apply it to the second scenario. So friction here is still 12. So the new force minus away 12 will give us the resultant force. So the resultant force, same thing, FR equal to MA. So the mass 6 times the new acceleration 4. So FR will equal to 36. So the answer will be B. If you're okay, let's move on to the Newton's third law. Okay, so Newton's third law, right, basically keywords: action, reaction. For every action, there is an equal and opposite reaction. And the key thing to take note, right, action and reaction forces, they're actually acting on two different bodies. So the easier way to visualize it is always when you push the wall. Okay, right now, if I push against the wall, right, you'll feel the pushing back forces. So these two forces, I will actually exert. So when I push the wall, so actually I will exert the force to the right on the wall. So the wall will actually push me back. So there will actually be a to the left force that the wall exert on me. So these two forces will be the action reaction. So when body A exert a force on body B will exert an equal but opposite force on body A. Okay, so for every pair of the action reaction forces, right, they will always be equal in magnitude. They add on different bodies. See, the action force is on body B, whereas the reaction force is adding on body A. And they're opposite in their direction. And most importantly, these two forces must be the same type. Like in these cases, it's the push, so it's contact force. So the reaction is also a contact force. So we can elaborate by this question over here. So a student is asked to draw an example action-reaction pair of the force described by Newton's third law. So this is the figure drawn by the students. So if you look at this force, reaction force on the book and then weight on the book. So the teacher states that this one does not show an action-reaction pair of the force. She added that the force in the action-reaction pair they have similarities and differences. Okay, so what would be the two ways in which the action-reaction pair, these two forces in action-reaction pair are identical? So if we look at the characteristics for the action and reaction forces, the one that they're identical from their characteristic, so you can see that they must have the same magnitude. So the size of the force is the same. And as I mentioned just now, they must be the same type of force. So if one is a normal contact force, the other one is also normal contact force. If one is a gravitational force, the other force is also gravitational force. So action and reaction must be equal in magnitude, and they must be the same type of force. So then two ways they are different. So if you look at that, the two ways that are different, they must add on different bodies. And in terms of direction, they must be opposite in direction. So basically, they'll be adding on different bodies and they'll be adding in different direction. Be very specific, is adding in opposite direction. So if you base on this characteristic, right, we look at these two forces drawn by the student. So one of the very easiest way to check okay, although these two arrows, right, it looks okay, they are equal in magnitude, they're opposite in direction. But if we look at the next point, they must add on different bodies. So this reaction force is adding on the book. So the book is the body. Then whereas weight of book. So weight of the book, right, is the gravitational force. Exerted on the book by the earth. So if you see that, this force, the body is adding on, right, is also the book. So both forces are actually adding on the same body. So they cannot be the action-reaction pair. So for C, if you want to describe one action-reaction pair shown in this figure, right, we can either write the reaction force for this, or we can also write the reaction force for this. So the reaction force on the book. So this is basically again, if I write out the whole thing, this is the normal contact force. Exerted on the book by the table. So usually when we write out this whole thing, right, we will know that we'll be able to see the one that is adding on. So that's our body A. The one that is actually providing the force, the one that's exerting the force. So that will be our body B. So once you identify your A and B, to write the reaction force, right, actually you just need to flip. So the reaction force for this will be normal contact force exerted on, so you flip these two, will be exerted on table by the book. So that will be the reaction force for this force. So similarly for this, gravitational force exerted on the book by the Earth. So this is A, this is B. So if you want to write the reaction force, we flip. So its reaction force will be gravitational force exerted on the Earth by the book. To state the direction of the force. In this case, we're just describing the force, so I think should be okay. Yep. Let me show you guys the phrasing. So the weight will be the gravitational force of Earth on the book. So you see this is your A and your B. So the right direction, we flip the two. So become gravitational force of book on Earth. So similarly, the contact force of book on table, then the direction contact force of table on the book. Okay, so I'll go through the next few parts. So this part is actually on the free body diagram. So basically, it's a tool that helps us to understand all the forces and hence allow us to find out whether the object is in equilibrium or whether it's the forces are unbalanced. Then we can use our Newton's second law to actually help us find the force or find acceleration. Okay. So the last two parts. So basically, we're looking at friction and then free fall for the air resistance. Okay, so I think friction should be quite okay. Advantage and disadvantage, and how do we reduce friction? So something that I want to highlight is for the friction for the wheel, right? Okay, if it's an engine powered wheel, right? When we have the rotated this way, right? When we actually rotated this way, because the wheel actually will push the ground back. So because of that, right, its tendency, that means its supposed movement is this way, and hence the friction is in opposite direction. So it actually will be this way. And this is actually the force allow the wheel to actually move forward. But whereas if we're looking at the free moving wheel, if you're looking at the free moving wheel, right, you can imagine that the wheel by right is not moving. So then do something. So if it's actually not moving, and when we actually push it, so when we push it, this portion here will being pushed forward. And because it's being pushed forward, the tendency is to go forward, and friction will oppose the motion. That's why friction will be backwards. And this will actually cause the wheel to turn this way. So as such, right, you can see the two wheels will be turning in the same direction. Okay. So basically, make it very simply, if it's an engine powered wheel, friction will be the same direction. Engine powered wheel, friction is in the same direction as motion. Whereas if it's a free moving wheel, so friction is opposite direction to the motion. Should be like the other cases that we learned. So friction is acting in the opposite direction to the motion. Okay, so next, let's move on to the last part. So for the last part, we're looking at the object falling. Okay, so we have the object falling, right? We always need to consider two scenarios. So first scenario, when we ignore air resistance, or we say that air resistance is negligible. So when air resistance is negligible, right, this case we say the object is free fall. So when it's free fall, okay, so free fall, right, is always in the absence of air resistance. So free fall occurs when the object falls under the sole influence of gravity. So there isn't any air resistance. So if the object is free falling, since weight is the only force, so our resultant force will equal to the weight. So ma will equal to mg. So you see, I can cancel out the mass. So the acceleration will always equal to g. So the mass actually will not affect the graph. So all the objects, when they are free falling, they will be accelerating at the same rate. So value A will equal to G. So if there is air resistance at the start, here, acceleration will still equal to G when our air resistance is equal to 0. But as it continues, right, our air resistance will actually increases as the velocity increase. So this is an important concept. When our velocity increase, air resistance will increase. So as a result, our resultant force will start to decrease. So if our resultant force start to decrease, our acceleration also decrease. So A will decrease us until it become 0. So when our A equal to 0, so when the weight equal to air resistance, A equal to 0, so that our V become constant. So this constant velocity is known as the terminal velocity. Okay. So previously, right, if it's free falling, mass doesn't matter. But if there is air resistance, when the object reach terminal velocity, W must equal to air resistance. So hence, the heavier the object, right, then the greater its weight. So that means that it will take a longer time for velocity to increases until air resistance equal to the weight. So this will result in a higher terminal velocity. Okay, so summing up, so larger the mass, larger its terminal velocity. So eventually it will accelerate for a longer time, you'll reach a higher terminal velocity, and you continue to fall with that higher velocity. So if both of them drop from the same height, right? So that will actually means you will reach the ground faster. So shorter time to fall the same distance. So to remember this part, you can always visualize if you're dropping a stone versus a feather. So the feather will reach a terminal velocity very fast because of its mass is very little. Whereas a stone, right, it will keep accelerating until you reach much higher terminal velocity. You'll continue to fall with that high velocity and hence you'll reach the ground faster. Whereas a feather is still going down with that very slow terminal velocity. So this is something you can take note. This is like one of the very popular MCQ question. Okay, so this was some of the example for free fall and the graph. So air resistance. So air resistance depending on the speed and also surface area. So the important concept we covered just now for terminal velocity. And the one we are saying just now How will mass affect the terminal velocity and hence the entire journey? Okay, so something to take note for this portion. So one of the commonly asked question in quite a few years MCQ, right? Okay, sorry, quite a few years open-ended question is they ask us to describe in terms of forces, why does the parachutist reach terminal velocity eventually? So usually this will be like the answer that we're looking for. As velocity change, as our velocity increase, air resistance will increase. So this will means that the downward resultant force decrease. Acceleration decrease. So this one explain, right, why the graph instead of straight line, it become a curve because of decreasing acceleration and hence decreasing gradient for this portion. And then eventually for the constant velocity part, so it will be the second paragraph. So this is when our air resistance finally is equal in magnitude to the weight. So the resultant force becomes 0, acceleration becomes 0, then velocity become constant, so known as the terminal velocity. So for the second part, if the parachutist open the parachute, a sudden increase in the outward force, and hence this resultant force adding outwards. While the parachutist is still falling down, is still coming down, if it has a resultant force that is acting outwards, right? This resultant force will cause him to decelerate. Decelerate and still in the same direction, so it will cause him to decelerate downwards. So that's actually what allowed the parachutist to slow down until it's relatively slow, it's safe enough for him to land. Okay, so this will be the explanation in terms of the process. Okay, so that will be like the key concept for our dynamics. Look at the last question, the last examples. So two objects have the same size and shape, but one is lighter than the other. So this is the one we're looking at just now. If they are free falling, they will fall at the same rate. They reach the ground at the same time. Okay, then this one you just say that they are dropped from rest in air. So in this question, they never say that air resistance is negligible. So we can consider the presence of air resistance. And because they have different mass, so the heavier one should be able to reach a higher terminal velocity and hence should be able to reach the ground faster. So you can look at the statement. So the lighter one has the same initial acceleration and the same terminal velocity. So same initial acceleration, right? This part is correct. Because initially when A is 0, when our air resistance is 0, everyone will have the same acceleration. But then the second part, same terminal velocity. This portion will be wrong already. Because terminal velocity then will be dependent on the mass and hence the weight. Lighter object has the same initial acceleration and lower terminal velocity. So yep. So the lighter one will be able to attain the terminal velocity faster because it's smaller weight. So that whereas the rest, the first part already wrong. And hence the answer will be our B. Okay. So we have finished the notes part. So you can let me know if you have any question. If not, then we'll take about 15 minutes to try the practice question. So in the practice question, we have the 4 MCQ and short structural question. So you can give a try first before we start to go through. I think we can give about 10 minutes. Those questions are quite short. So we can start going through the question at 9:15. So meanwhile, if you have any question, then you can type in the chat and let me know. And if you finish the practice question, you want to check your answer, you can message me as well. Okay, we have 3 more minutes. If you already finish your MCQ, you can send me your answers first. Okay, time's up. Okay, we shall check the answer for MCQ first. Okay, guys, you can check your answer for the 4 MCQs. And please let me know which question shall we go through. Okay, I request for question 2 and question 4. Do I have any other requests? We can move on. So for question 2. Okay, so the ball is dropped from the top of a 125-meter tall buildings. What is the time taken to fall to the ground? Take G to be 10. Okay, so the method, right, actually is quite similar to what we have just now. So basically, we are still using our V against T graph. Okay, if I draw a larger one over here, V against T. So by the time we reached the ground, right, if I let this time here be T, okay, it will reach a velocity V. And this V here, because A equals to V minus U over T, so my V actually will equal to 10T. So when you reach the ground at T seconds, the distance traveled, right, will be this area under the graph. So this part here, actually half times base times height will equal to the distance 125. So we actually have 5T squared equal to 125. So if I solve it, so T squared will be 25. So T will actually equal to 5 seconds. Basically, this will be the working. So we're still using the V against T graph, and because it's free falling, if the time is T, then the velocity you reach the ground, right, should be 10T. And then hence we can use it to form the quadratic equation to solve for the time. Okay, if you haven't finished copying, right, you can take a picture first. Okay. Okay, then we'll move on to question 4. Okay, so for question 4, so we have the objects of mass m. We're traveling to the right with a velocity 2v. Then another object of the mass 2m traveling to the left with a velocity v. Okay, which statement is true about the both object during the collision? So the inertial, right? Remember, this one is linked to mass. Mass of the object will always be constant. So during the collision, no matter how hard they collect, unless they lose a piece of them, the mass will remain the same, the initial will remain the same. That's why this one will be wrong. Then B, the sum of total energy in the store decreases. But then questions just tell you that assume no energy transfer. So no energy transfer, the total energy that they have in their stores should still be the same. That's why this one is also wrong. They experience a deceleration of the same magnitude. Okay, so this one here, the acceleration will depend on the resultant force. But even they experience the same resultant force, they have different mass. And hence, the acceleration will also be different. So the last one, during the collision. So when n hit into 2m, when they collide, they will exert the force on each other. So basically, n will exert the force on 2m. Then for this action, there will be a reaction. So these two forces are action reaction, and hence the two forces are the same in magnitude. And hence this part will be our last option, D, will be correct. So again, you can take a picture of the explanation first. Okay, and then let me know if you still have any question for the MCQ before we move to the structural question. Okay, I think everyone is okay. So if we go on to the structural question, same thing, we'll do the question, right? Underline the key information. So if you have the rockets, it has a total mass 1.2 times 10 to the power 5 kg. So then figure 1.2 shows the upward thrust on the rocket with a time in the first 40 seconds after the launch. So the G is taken as 10. So part A, calculate the weight. Okay, use our formula. W equal to mg subbing. Okay, I think this one should be straightforward. So at the point of launch, the rocket does not take off immediately. State the time which the rocket starts to take off. So remember, adding on the rocket, there is the weight, which we find out is 1.2 times 10 to the power 6. So in order for you to take off, right, minimally, the thrust here should equal to the weight. So any higher than that, there will be a upward resultant force. So then this will allow it to accelerate and hence take off. So we're looking at where the thrust minimally must equal to 1.2 times 10 to the power 6. So from the graph, right, 1.2, 1, 2, 3 over here. So this point onwards, the thrust will be higher than the weight already. So then that will give us a resultant force for it to take off. So the answer will be at the 6 second. So this is the time where the upward thrust is equal to the weight. Okay, therefore C, assume no change in the mass, calculate the acceleration of the rocket at t equal to 30 seconds. So if we go back to the graph at t equal to 30 seconds, so the thrust is over here, 4.8 times 10 to the power of 6. So if you know the thrust is 4.8 times 10 to the power of 6 and the weight is 1.2, so you can actually put it together. So you can put it together to find the resultant force. And then from there, resultant force FR equal to MA to help us find the acceleration. So you can check your working. Whether you get it correct. This will just be putting the values and then calculate the value for A. And because the question tells us that no change in the mass, so for M, we'll still be using the same value. So 1.2 times 10 to the power 5 kg over here. Also okay already for the last part. So 30 seconds after the launch, the total weight of the rocket and the content decreases significantly as the fuel is being burned off while the thrust remain the same. So if you look at the box again, right, the thrust remains the same, but then our weight is actually decreasing. So FR, the resultant force, is actually the thrust minus the weight. So if the weight start to decrease very significantly, so guys, if you look at the relationship, this remains the same, but this portion become much smaller. So we minus a smaller number. On the other side, our FR will start to increase significantly. So then FR is MA. So that means that our acceleration will also start to increase. So this will link to the motion. So if acceleration start to increase significantly, so the rocket will still be accelerating. But previously, right, its acceleration will be like a constant value. Yeah, because like the process is the same, then it's constant. But now when it's decreasing, FR start to increase. So the acceleration will start to increase. So the rocket will still be accelerating, but it will be accelerating at the increasing rate. So you know, just mention that there will be increasing velocity because from the acceleration, we already know that it increases. But it's like previously A is constant, so its velocity increase at constant rate. Right now, when our A increase, when our resultant force increased, our A will increase. So that's why you got to mention the increasing acceleration. Okay, so if not, so that will be the end of today's physics WA2 revision. So I hope that this lesson has been useful to you. So if you need more help, so you can consider signing up for the regular group class. So just leave this one on over here. So these are the schedule for the chem class and physics class. So as well, there will be like other subject for Set 3. So there will be the AMATS class, EMATS class, as well as for English. Yeah, so if you're interested, you can just scan the QR code. Otherwise, that will be all for today. If you have any question, you can ask me. Otherwise, that will be all. So see you guys.